Okay, hi everyone again. In this video, we will dive into the subject of non-zero temperature lattice QCD after having convinced ourselves in the past video that thermal non-abelian quantum field theory do demand investigations that are based on non-perturbative techniques, such as the lattice approach. In this video, we will start with the basics of lattice simulations at non-zero temperature, and then we will move on to discuss the type of phases of Yang-Mills as well as full QCD matter in the two limits of very high and very low temperature. We will see and discuss how can we distinguish these phases based on global symmetries of the underlying theory, and this will lead us to the definition of observables that we can measure in our lattice simulations in order to make sure on which side of the phase boundary or transition that separates the different phases we are when we start our simulation with a given set of input parameters. And in particular, it will allow us to locate and classify the phase transition that separates the relevant phases. Okay, so we are at this stage in the plan of our course. We are discussing critical phenomena in the framework of non-zero lattice QCD and the relevant symmetries that match these critical phenomena. But as I said, let's start from setting up the stage for a non-zero simulation in lattice QCD. At non-zero temperature, you need to know that we can introduce this temperature in our path integral formulation of QCD by starting from the partition function that describes a quantum mechanical statistical system in contact with a heat path that is at non-zero temperature. And then following a derivation which is completely analogous to the one that has led you to the definition of the t=0 path integral formulation for a Euclidean quantum field theory in terms of fermionic and gauge fields, you arrive at an expression for the generic expectation value of an observable or at an expression for the partition function and the action that look exactly like the t=0, their t=0 counterpart, apart from the fact that now, as you can see in the formula for the action, the temporal direction is compactified with the Euclidean time, which is restricted to range between 0 and beta, which corresponds to the inverse temperature. And that is the unique difference with respect to t=0, together with the fact that you want to ensure the correct statistical behavior of the fields in terms of which your action is defined by enforcing periodic or anti-periodic conditions in this temporal direction over which the lattice has been compactified. In particular, to have bosonic description or a bosonic statistic, you want your fields to be periodic in the finite time direction, and for a Fermi-Dirac type of statistics, which is the correct statistic for fermionic degrees of freedom, then you have to ensure anti-periodic boundary condition in this toroidal manifold that you have built in the lattice. Because actually, if you think about it, in a two-dimensional example, our lattice would then look exactly like this torus. And in the following, we will study the different lattice observables that can be measured on that torus. The other important thing I want to mention in this slide is that by looking at the formal equivalence between the quantum mechanical statistical system in a heat bath and the Euclidean quantum field theory, you can read out the relation that connects the temperature to the extent in the temporal direction of our lattice, which is the product of the lattice spacing and the number of sides that you have along the temporal direction. Of course, then the lattice spacing is controlled by the coupling in our theory, so by beta in this case. And this is how you tune the temperature in your system. You see that you have two knobs that you can play with. You have the temporal extent, by changing which you can have some discrete steps in temperature, or you can change the coupling beta, which reflects into a change of the lattice spacing, which then changes the temperature. Another important thing to keep in mind is that you want the typical length scales that you can define in your theory are separated by a chain of inequalities of the type that I wrote on the slide. So particularly, of course, your smallest length scale is the lattice spacing. And then what you want is that this is way, way smaller than the largest correlation length in your system, which in turn should be much, much smaller than the spatial linear size of your lattice. And then this is something that holds already at t equals 0, how to transpose this chain of inequalities at non-zero temperature. This is done by observing that in that case, the largest correlation length in the system is connected with the smallest screening length that you have in the system. We will have a dedicated lecture, a dedicated video about screening and screening masses and lengths. But what you need to know here is that this scales like the temperature for large temperatures. So the way you transpose the chain of inequalities in order to figure what is the scale separation that you want your lattice simulation to be enforcing, then what you have is that the lattice spacing must be much smaller than the temporal extent of the lattice, which is the inverse temperature, just the scaling of the corresponding screening length at high temperature, which should be much smaller than the spatial extent of the lattice. So how do we achieve this? By having a large so-called aspect ratio. By aspect ratio, we mean the ratio of n sigma over n tau. And non-zero temperature simulations are simulations that are going to be that are normally run on asymmetric anisotropic lattices, unless you go for anisotropicity in the lattice spacing, which is a subject that we will touch when we discuss the equation of state. But let's focus on isotropic lattices now. Then your simulations will be run on lattices which have distinct sizes for the temporal side and for the spatial side, and you want this chain of inequalities to be fulfilled. Last important point, when you want to take the continuum limit and you are studying non-zero temperature, you want your temperature to be held fixed while you take the continuum limit. And this, for example, entails that when you send A to 0, then n tau has to go to infinity in parallel such that the temperature is held fixed. All right, and as I said, the next step would have been discussing the phases that you encounter in, for example, Yang-Mills theories. What we know about non-abelian or Yang-Mills theories is that they are characterized by confinement on the one edge of the energy scale and asymptotic freedom at the other edge. So particularly we have confinement at low energies and we have asymptotic freedom at high energies. All right, and let's think now first about the low T limit where we know that we have confinement. And what can be explicitly studied is that the strong coupling corresponding to the low T limit of lattice Yang-Mills theory does indeed confine quarks. How do we see that? We see that in the linear growing behavior of the anti-quark static potential with respect or as function of the interpair distance. And this is a consequence of the highly nonlinear dynamics of Yang-Mills theories. What happens in practice is that you have flux tubes that are formed in agreement with the non-abelian version of the Gauss law by the color-filled lines that connect the two charges in the vacuum that in the case of a Yang-Mills theory are not spreading radially as they would in a typical QED dipole spatial pattern, but they are rather squeezed in a tube-like structure. Okay, this we sort of know empirically because we cannot observe free color degrees of freedom in nature at our standard conditions, but how to see confinement at work in a theoretical framework for the theory. What we can do is we can produce such a pair of static sources in the vacuum. So we create the QQ bar pair at x mu equals 0, then we can separate them at a relative distance r, and then we can hold this charge configuration in time for a very, very long time in the limit of t that goes to infinity. Please note that I'm using t for temperature and for the distance in time direction between the charges, but it should be obvious what I'm referring to. And then we, as a last step, let the Q and Q bar pair annihilate by bringing the two sources back together after having held them for an infinite amount of time. How to write that in a formula? You have it on these slides. You have the Euclidean amplitude for the quark-anti-quark creation, infinite time evolution, and annihilation. You see that basically this is the corresponding expectation value, which then should match the negative exponential of the potential as a function of capital R, which is the relative displacement between the sources, and T, which is the temporal extent of the evolution, where the current in this expression is describing the closed word line of the creation and annihilation of our static pair. Then what we have arrived at is an expression for the static potential, but in the continuum, because the formula I had on the previous slides were in the continuum. And here is the potential written down explicitly in this language. However, we want to look at the low T limit. This corresponds to the strong coupling limit. And for a strong coupling expansion, we need as a starting point, rather than this expression, its lattice counterpart, particularly the lattice counterpart of this word line that along which the static QQ bar pair evolves, which is nothing but what we call a Wilson loop on the lattice. And by using some properties of group integrals, this quantity here can be evaluated in a strong coupling expansion to leading order. And this is where we get the famous area law for the Wilson potential. So the important result that the potential, V as a function of R, is linearly depending on the interpair distance with a coefficient, which is what I'm indicating by square root of sigma in this case, which is related to the logarithm of the square of the coupling, and which is what we call the string tension. This is a very important result that was obtained already in the 70s, and it holds in the at leading order in the strong coupling expansion. And now let's abandon the low T limit and talk about what happens when we heat up pure Yang-Mills. What happens is that you go from this confined phase into a so-called gluon plasma phase. This is the state of Yang-Mills matter for large enough temperature. What are the expectations on this gluon plasma phase? We know that this will be characterized by deconfinement, and based on the fact that confinement is signaled by a linearity in R of the potential with a proportionality constant given by the string tension, we understand that when we move to the gluon plasma, the string tension should vanish, and it should do that exactly at the phase boundary. And the other characteristic of the quark-gluon plasma phase is color screening, meaning that a fundamental quark that you would introduce in such a gluon plasma will have its color field short-ranged and exponentially screened after some typical length scales. And now that we know that there are these two phases, we should discuss together how can we distinguish the two phases in this theory. And in order to do that, we can consider the free energy differences between the system that does contain such a static quark-anti-quark pair separated by some distance r, and the system that does not contain that pair, or the system at which basically the two pairs are not, the two quarks are not existing. If we compute that difference, we see that in the confinement regime, while the temperature goes to 0, then the difference between the two cases is infinity, because it takes an infinite amount of work in order to separate the two sources to a distance which goes to infinity, which is what I mean by this symbol over here. On the other hand, in the deconfinement case, there is not such energy cost. The two sources are free to begin with, and therefore the free energy difference goes to zero as t goes to infinity. So somehow we see that we can distinguish the two phases based on this energy difference, which in turn can be written as the negative logarithm of the ratio of the two corresponding partition function. And if we write that down explicitly, we can understand what is the corresponding relevant lattice observable. Why? Because a persisting static QQ bar pair in the lattice at t greater than 0 as its lattice counterpart in a pair of Wilson lines that are wrapping around the compact t direction. How do you understand that? These are static quarks. We know that for static quarks, we can construct something which in lattice is called a hopping parameter expansion. And we know that at the leading order in that expansion, propagator is just a product of a straight line of gauge links. And this is exactly what's happening here, just that the gauge links are all aligned along in a time slice in the temporal direction, and they build together what we call the Polyakov loop. Not just one of them, because we have a static source and a static anti-source. So one of them corresponds to a Polyakov loop, and the other one corresponds to the dagger of the Polyakov loop at a different time slice. Okay, then we have a way to rewrite the ratio of the partition functions that then matches back to the free energy difference through which we distinguish the two phases. Then if we also use translation invariance, which is in place on our lattice, we observe that the ratio of the two partition function defines nothing but exactly the expectation value of the correlator of two Polyakov loops at some distance r. So it's basically a rewriting of what we had in this expression just by using translation invariance to set the coordinates to 0 and r respectively. And in the limit of r that goes to infinity, we have cluster decomposition that ensures that this expectation value of the product is just the product of the two expectation values, which then leads to the absolute value square of the average of the expectation value of the Polyakov loop. It follows from this and from the fact that the difference of the free energies is infinity on one phase and 0 on the other phase, and it is connected via a logarithm to the ratio of the partition function, that this quantity is what we call an ordered parameter for the deconfinement phase transition. What is an ordered parameter? It is an observable which is 0 in one phase and non-zero in the other phase. And now we have just realized what that observable is. Actually, you can find out with simulations that there is indeed a true phase transition in pure Yang-Mills, for example, with 3 colors. And this is a transition that happens at a temperature of about 270 MeV. The next thing we want to do after we understand that there has to be a transition, because we have looked at the high T and at the low T limit, and we have seen very different behaviors, and we have also just understood what observable can distinguish the two phases, is we would like to classify this transition. So being able to say whether it is a first order, a second order phase transition, or some continuous phase transition. And to that, we need to ask ourselves what is the relevant symmetry whose breaking is connected with the change in the behavior of the order parameter that we have just discussed. And this symmetry in the pure Yang-Mills case is center symmetry. Its breaking is in fact indeed associated to the confinement. And I now need to tell you what center symmetry is and how it comes, how it happens that this is broken with the temperature in correspondence to the phase transition. Center symmetry is connected to topologically non-trivial gauge transformations with the boundary conditions that are expressed in this relation. So you have omega, which is a matrix in SU3, and this is the gauge transformation, and it is made topologically non-trivial by the fact that it satisfies these boundary conditions where you see that there is a small z, which is a constant element in SU3 to begin with. Then let us ask ourselves what happens to our theory. So what are the quantities that are left invariant, or what are the quantities that vary under topologically non-trivial gauge transformation of this type? One thing that comes to mind is that if this is a boundary condition, then the plaquettes that are living close to the boundary, which then are part of the plaquettes that we sum up in the gauge action, might be affected. So let's see if that is true and what conditions should the Z fulfill in order for these plaquettes to be left invariant and the gauge action to be left invariant as a consequence. If you think about temporal plaquettes in this last time slice close to the boundary, and you look at the boundary conditions for the gauge transformation in temporal direction, you understand that the two temporal links that appear in those kind of plaquettes are going to take a factor of z and z minus 1 respectively. So we get a transformed expression for the plaquette that contains this z and z minus 1, and they do not happen to be close to each other because you need to follow the path of the plaquette, and then you need to transform the links sequentially, and you have the transform of the spatial link in between. However, if this z and z minus 1 would be not just constant SU3 elements, but elements of the center of the group, which we know are those elements that commute with any other element in the group, then they would be able to go through the other quantities in the transformed temporal plaquette and just cancel each other, leaving the plaquette invariant. So this is one observation, and the next is that these are the only plaquettes that are going to be affected by the non-triviality, the topological non-triviality of this gauge transformation that we are doing, and then the gauge action would be invariant under the same circumstance that z and z minus 1 belong to the center of the group, because no plaquette would be affected by this transformation. There is, however, a quantity, and this is the important bit, that that does not close in a topologically trivial way, and this is the Polyakov loop that picks a factor of z and lives with that factor of z. And this is what makes the connection between the breaking of this symmetry and the Polyakov loop being the correct order parameter for the phase transition, because that is going to be 0 in the symmetric phase and non-zero in the phase in which this symmetry is broken, based on the relation that you can read out in the slide. All right, so what have we learned? There is a thermal transition in Yang-Mills theory, and this transition signals the spontaneous breaking of the center symmetry, for which this quantity that we have just introduced, the Polyakov loop, is the order parameter. I want to add to this that an analogy can be constructed to a three-state spin model with spin variables that belong exactly to Z3, that lives on the side of a three-dimensional spatial lattice, and this also undergoes a transition at some value of the coupling, just like pure Yang-Mills in SU3, where, by the way, the transition is first order, but we will get back to this. And one important point, as we said, we want to see what observable we want to measure in our lattice simulations in order to locate and classify the phase transition, is that the correct determination of the expectation value of the Polyakov loop in a finite volume is a delicate matter, and it is actually better to look at this quantity instead. The reason for it being that the average, the expectation value of the Polyakov loop is bound to vanish for sufficiently long runs, because at some point there will be a tunneling between the different center sectors, which is only suppressed as V is sent to infinity. And only in that case we can get a good approximate determination of the expectation value of L. But we need to live with tunneling because we simulate at infinite boxes, and this is a finite size effect which corresponds to an uncontrolled systematic, and therefore we should look at the absolute value instead. Okay, moving on to the relevant symmetry for the more intricate case of full QCD, where we also have the fermionic part of the action to pay attention to. The relevant symmetry there is chiral symmetry, and what happens is that this symmetry is restored rather than broken when you raise the temperature. And this is the other important non-perturbative effect which is triggered by a non-zero temperature. To understand that, you want to look at the fermionic part of the action, and we can simply look at its continuum Euclidean version when we have NF fermion flavors in our theory, and then we have this expression, and then we want to focus on some global symmetries of this fermionic action, in particular those connected with vector and axial rotations of the corresponding spinors. So we take the spinor and we send it into a transformed spinor, either via NF square vector transformations of this type, and in this case we can safely figure out that the massless theory is symmetric under this kind of transformations. Actually, for the first two you can even have degenerate non-zero masses and still the symmetry would be fulfilled. And the theory is also symmetric under chiral or axial rotations, which are called this way because they mix left and right components in the spinors, and they are defined by this set of equations. So with this in mind, for the massless theory, we can acknowledge the fact that the overall symmetry group for the theory certainly includes the SUNF left times SUNF right times U1 vectorial corresponding to the conservation of the baryon number. However, there is one piece of the overall symmetry which is broken at the level of quantizing the theory, which is the U1 axial symmetry. And this is due to the anomaly which you maybe have heard about already. So the axial anomaly, due to the non-invariance of the fermion integration measure, is already restricting the symmetry group to a smaller group. And then you might want to simulate actual quarks as we know them in nature, and these are massive particles, which leads to a further breaking of this subgroup of the symmetry group into SUNF vectorial times U1 vectorial, with this part of the symmetry group that cannot be broken down further, as we know from theory for the vector-like coupling. And then you can have non-degenerate masses. So you can consider, for example, the fact that the up and down quark have different masses. This is not normally done because their masses are very similar. So normally you have them degenerate, but then you can certainly introduce in the simulation a third quark, a strange quark, and this would be non-degenerate with the other. And what this means is that we have a further breaking of the chiral symmetry into basically UV1 pieces, and we have enough of them. All right, so this are symmetries at the level of the action. Next thing we want to ask ourselves is whether the ground state is also chirally symmetric and reflects this symmetry group for the fermionic action. We need to, at that point, distinguish between different possibilities for the breaking of such symmetry. We might want to consider the explicit breaking, which comes from the fact that the fermionic flavors or the quarks have a non-zero mass. However, as said, the up and down are very light. They amount to a very much smaller mass than the mass of the corresponding of the nucleon. And even if we put in the breaking due to the non-zero strange mass, this would be just a 10% effect. So this is as much explicit breaking we have in the actual theory, and that would certainly not be enough to explain some important empirical fact, which is the mass difference between n and n star in nature, which is definitely too large to be attributed to the small explicit breaking due to the non-zero quark masses. This is why we talk about chiral symmetry being spontaneously broken. Just like the center symmetry was spontaneously broken at high temperature, now we talk about chiral symmetry being spontaneously broken at low temperature. And if there is spontaneous breaking, then the Goldstone theorem is telling us that we will have NF-1 many pseudo-Goldstone bosons that will make their appearance and that will would want true massless modes, but only in the chiral limit. We can also construct a low energy effective theory called a chiral effective theory that from which we can learn about the behavior of the system with respect to chiral symmetry. Here I have the Lagrangian. In this Lagrangian you have a mass matrix which contains on the diagonal the matrices of the different fermionic flavors, and F and B are low energy constants, and this Lagrangian is characterized by its invariance under chiral rotations. What this is just a ferromagnetic spin system equivalent to O4, where basically the masses are playing the role of the magnetic field in the corresponding spin system. One can bring the analogy one step forward and realize that the real part of the trace of m times u plays the role in that system of the magnetization, and its counterpart in QCD is the chiral condensate, which is the expectation value of psi bar psi. And we have thermal restoration of chiral symmetry, meaning that increasing the temperature or correspondingly the coupling, at some point this quantity will become zero. However, the transition, which is then found in this way by looking at the value of this ordered parameter, magnetization-like ordered parameter, weakens and becomes crossover when you let the involved masses increase. So again, we have a model to which we can go for an analogy where we observe the same kind of trend, just like the three-dimensional spin Z3 model for the center symmetry. So we have identified the order parameter, also in this case, by the analogy with the chiral effective theory. This is the so-called chiral condensate. It is an exact order parameter in the massless limit because it signals restoration by becoming zero, by vanishing. In the massive case, it is only an approximate order parameter, but still it decreases it decreases significantly at the critical or pseudo-critical temperature. Okay, of course, we have to care about that we renormalize chiral observables, and the same case, the same is valid also for the gauge observables, even though we haven't discussed it explicitly. Then we want to regulate the ultraviolet divergences, additive and multiplicative renormalizations. And in this box, I'm just telling you how can you combine the light quark condensate with the strange quark condensate in an NF equal 2+1 simulation in order to obtain a final order parameter which is free from ultraviolet divergences. And then, but this is not specific to chiral symmetry, is exactly what you also do when you look at the breaking of the Z3 symmetry. You want to look at the susceptibility of the order parameter with respect to the corresponding thermodynamic or microscopic parameters, so in this case the mass of the fermions, and you will observe that this peaks at the transition or crossover temperature. Crossover is the name by which you call a continuous phase transition where you don't have jumps or non-analyticities in the first or second derivative of the partition function or in the partition function at all. Okay, and then correspondingly to chiral symmetry restoration, there are some other important aspects that you might want to look at in a lattice simulation, and these concern the degeneracy of species, in particular of what we call chiral partners. So what is that? We have particles like the pion or F0 or the eta and so on. And we can build families of so-called chiral partners or axial partners. These are masses that would be degenerate if the corresponding symmetry would be respected. And the degeneracy is instead lifted by a spontaneous breaking of the corresponding symmetry. So according to the pattern in this figure, you have that once the corresponding symmetries are restored, then the correlators become equal and therefore also the masses. And the same kind of reasoning can be applied to chiral symmetry restoration as well as to the effective axial symmetry restoration, which is also expected at very large temperatures. And it is not clear whether these temperatures are the same or of the order of the chiral symmetry restoration temperature or higher. Okay, I think we now have an idea of chiral symmetry breaking, but in order to get a better intuition, we can also use a semi-classical argument for why chiral symmetry breaking is absolutely necessary for the vacuum to support bound states and therefore to confine. The chiral symmetry breaking can be shown, and this was shown by Kasher long ago, to be necessary in vector type theories that are confining quarks, just like QCD, because you can consider a chirally symmetric Lagrangian and some massless matter fields. And if you assume, as it is the case, spin independence of the confining force and also the existence of bound QQ bar pairs in S-wave states, then semi-classically confinement, so the fact that this Q and Q bar can only exist in that bound states, ensures the fact that in the word line of the, for example, Q constituent of that pair, there has to be a turning point, and the spin independence of the force in turn requires that at that turning point there has to be a change of sign in chirality. So chiral symmetry breaking is dynamically induced by the fact that the theory is confining and the confining force is spin independent. So what happens is that at the turning point, the Q must pick a unit of chirality from the vacuum. That's the only way. And by that, we also understand why the chiral condensate is an ordered parameter for this chiral symmetry breaking, because for this to be possible, the vacuum must have an indefinite chirality as a condensate of psi bar psi. Okay, so this I think is a nice semi-classical argument that one can use in order to argue for the necessity of chiral symmetry breaking at low temperature. This is not a priori obvious based on the T-dependent strength of the attraction between the sources in the pair, but for quarks in the fundamental representation, it turns out that screening forces are not strong enough to support condensate, and then you have chiral symmetry breaking explicitly at deconfinement. And this was checked for light quark propagation in quenched gauge field background, for example. Okay, and then we can make one further step in connecting the order parameter for chiral symmetry breaking with the extrapolated Dirac spectral density at 0. This, according to a very famous result, which goes under the name of the Banks-Kasher relation, that's explicitly relating these two quantities. The way one obtains this is by starting from the continuum fermionic Green's function, that is from the propagator, that can be rewritten in a spectral representation in terms of its eigenvalues and eigenvectors, in particular the eigenvalues and eigenvectors of the Euclidean operator IDM. We are building this, this relation in a Euclidean continuum version in order to keep it simple, of course. Then chiral symmetry expressed in this formula ensures that the eigenvectors will come in pairs and with eigenvalues that have opposite sign. And by using this property, by setting x equal y, by considering the trace of the propagator and evaluating this quantity on a gauge field ensembles and integrating over x, we get to this partial result on our way to the Banks-Kasher relation. And then the next thing we have to observe is that the chiral condensate is defined in the V to infinity limit and also in the chiral limit. And if we then take these two limits in the right order by sending the volume to infinity first and the mass to 0 afterwards, we can recognize that this quantity 2m over m squared plus lambda squared is a representation for a delta function. And we are left with basically the final result, which is very well known, goes under the name of the Banks-Kasher relation. One particular remark about this formula is that we can see how the dynamic of strong interaction is affecting the interspace, the distance between the eigenvalues, which in the free case would have been proportional to the inverse linear size of the lattice, and then it would have to go with the volume like this. But in fact, it does go with the volume inverse itself if we define the eigenvalue interspacing by the inverse of the density at 0. Yeah, all right. And then I think we have said enough about the relevant symmetries and their breaking or restoration with T in Yang-Mills and in full QCD. In order to be able to understand another very famous result, actually a plot, which goes under the name of Columbia plot, where we explicitly show the dependence of the order of the QCD thermal phase transition on the microscopic parameters of the theory, specifically on the quark masses. How should you read this plot? You can see that we have the strange quark mass on the y-axis and the light degenerate up and down quark on the x-axis. For it to be a phase diagram, you would need a temperature axis. However, this is basically projected down on the plane, meaning that each point on the Columbia plot is at the corresponding critical value of the temperature. And then what you indicate by the colors and by the position of the lines separating region of different colors is the order of the phase transition. Okay, so in the infinite mass limit, this is where we recover the pure Yang-Mills theory in this case, and we know we have just discussed that there is a breaking of the global Z3 symmetry, and we have identified the order parameter for that purpose. And in the opposite limit along this diagonal where all masses are sent to zero, this is what we basically have just discussed. This is the chiral limit where we know at some point the temperature will restore the global chiral symmetry, at least this subgroup of the global chiral symmetry, and an order parameter for that is the chiral condensate that we have just introduced. Let's stick to the plot and make more remarks because we have just discussed 2 points out of an entire plane. So we have chiral Z2 boundaries, which are the blue lines that are separating first order regions from crossover, a big crossover region. What is happening? It is happening that we have reasons to believe that the transition is first order, both in the pure Yang-Mills theory, also according to the famous Wetysky-Jaffe conjecture, and in the chiral limit of the 3 flavors based on an analysis by Pisarski and Wilczek. And the other thing we know is that a first order phase transition cannot be isolated. The jump must be absorbed and become smaller and go to zero. And this is what happens in the order parameter, I mean. And this is what happens when you tune the value of the symmetry breaking, corresponding symmetry breaking field, which is the mass coming from this bottom left corner and the inverse mass coming from the top right corner. And then many aspects of this phase diagram have been studied with lattice simulations. In particular, it has been studied that the width of the chiral first order region grows as a function of the number of fermionic species in the simulation. It is not yet clear if there is a finite size at nf equal 2 in that respect. And an important role can be played in that respect by the effective UA1 restoration at Tc or above Tc, because that sort of tells you how much symmetry you have in the system and whether you should expect here to have a first order phase transition or rather a second order phase transition. Another word of warning about this plot is that this is not based on continuum extrapolated result. Actually, the only point that we can safely locate on this plot is the physical point where we know since 26 that there is a crossover and not a true phase transition. And then another important remark is we know that the true up and down quark masses are very small, and therefore we can ask ourselves whether the transition at the physical point is affected by remnants of the chiral universality class, especially if this region shrinks to zero and we have a second order phase transition, in which case universality is in place. And this becomes a particularly relevant question when we want to switch on a non-zero chemical potential and asymmetry between the density of matter and antimatter, where you can build a 3-dimensional version of the Columbia plot, and depending on the behavior of these lines, which then span surfaces in the mu direction, we can argue about the existence or non-existence of the second order critical endpoint, which is one of the most sought for characteristic of the phase diagram of QCD in the temperature versus baryon or quark chemical potential plane. Why am I saying that the situation is still not so clear over here? Because if you run simulations, you pick a discretization, maybe you pick an unimproved discretization as we have done in previous investigation. You can observe that the precise location of the Z2 boundaries is cutoff dependent. It changes when you change the value of n tau and you tune the temperature at the critical temperature. Particularly, it shrinks in this case, the first order region, it enlarges in the other case, and therefore when you send the lattice spacing to 0, there are still, when I am just looking at this axis, so at the case in which the strange becomes infinitely massive and I effectively have only 2 flavor species in my system, 2 possibilities. The fact that there is still a finite first order region, or there is none, it shrinks to 0, and in that case I have necessarily a second order phase transition in the chiral limit, which leads to constructing different possible scenarios for this plot based on different expectations on the nature of the chiral transition in the chiral limit of the 2 flavors axis, which is the top axis in the plane. And yeah, for that, as I mentioned already, the strength or the effective restoration of the axial anomaly is playing an important role based on an argument obtained in the 80s by Pisarski and Wikzek. And then you can go ahead and look at which of the 2 scenarios is realized. And this you can do with lattice simulations, where you progressively decrease the mass of the light quarks. This would be the direct approach. You just sit on the top axis, you make the masses smaller and smaller, and you look at the transition and check what its order is based on techniques that I'm going to introduce to you in the next videos. However, this direct approach has proved to be very expensive because, as I mentioned in the introductory video, the Dirac metrics that we have to invert in the course of our lattice simulations is ill-conditioned and becomes more and more ill-conditioned as the mass is sent to 0. So with standard solvers, you have the significant growing costs in your simulations. Then one has to come up with a strategy for answering this question without having to simulate at very small masses. And here comes the statement of my introductory video when I told you that in the chiral limit somehow the situation becomes more critical. So in particular, in the case that the second order scenario is realized, you see that in the chiral limit we have a line of triple points at the coexistence of 3 different states for the chiral condensate that terminates into this red dot, which is corresponding to what we call a tricritical point or phase transition, which is also the meeting point of 2 second order boundaries, in this case belonging also to different universality classes. The question is, can we exploit the existence of that point in order to say something about the nature of the chiral phase transition? And the hope is that we can, based on the fact that as soon as we get close enough to that point, we fill the exponents and the universality of the transition at that point. So how do we achieve the goal of saying something about the transition in the chiral limit? We do that by running simulations in fixed parameter setup. For example, we can run an F = 3 simulation, and with some values of the temperature around the corresponding transition temperature, we can target this point in the Columbia plot and also find out in ways that I'm going to detail in the next video that this is indeed a first order phase transition. Then we can move to a different setup in terms of constituent masses, increasing both the mass of the up and down and the mass of the strange quark. And at some point, when these are large enough, we end up in the crossover region, meaning that if we make a scan in the temperature that in the meantime has grown, we can identify that this is not a true transition anymore, but rather a crossover. And by doing this, we can isolate the values of the masses at which we have a Z2 transition. I'm going to tell you explicitly how to do that in the next video. And then we can continue simulating along that Z2 line by locating it for every different masses set up, as I mentioned before, until we enter the scaling region of this tricritical point, where we are lucky enough to know what are the critical exponents, and then how should equilibrium thermodynamic properties of our system behave as a function of the distance to that transition. And with this, I am terminating this long video. I hope I gave you a feeling of how we go about simulating QCD at non-zero temperature, what are the relevant symmetries in the Yang-Mills corner as well as in the chiral limit, what are the corresponding lattice observables that you want to look at in order to identify the different phases that you have at low and high temperature, and in particular locate the phase boundary between the two of them and identify the order of the phase transition. How that is done in practice, well, if you wait for the next video, you will learn about it as well.